Hey everyone, and welcome. Today, we're going to pull back the curtain on something you might be using right now, even without thinking about it. The lens. From the glasses on our faces to the amazing telescopes that look out into deep space, the physics behind it all is actually, well, it's beautiful. And it all starts with a little number you've probably seen, but maybe never really understood.
So, let's start with this. You've probably seen something like it on a prescription from your optician, right? A little plus or minus sign, a number, and then this capital D. What on earth is that? Well, I promise you it's not just some random number. It's a very precise measurement of your lens's power. And by the time we're done here, you're going to know exactly what it all means. So to really wrap our heads around that number on the prescription, we've got to get back to basics. We need to understand what a lens is fundamentally doing. And you know what? It's all about bending light.
Okay, so what is the power of a lens? In the simplest terms, it's how much that lens can bend light. That's it. A lens with a really high power is going to bend light rays a lot, while a low-power lens just gives them a gentle nudge. So it's a measure of convergence, that's pulling light rays together, or divergence, spreading them apart. I love this phrase for it. It's basically the lens's bending strength.
All right, check out this diagram. It shows us exactly what's going on. Let's follow this light ray coming in parallel to the center line. The lens hits it and bends it down at an angle. We call that angle delta. Now the spot where that ray crosses the center line, that's the focal point. And the distance from the lens to that point, that's our focal length, which we call f. So think about it. What if we wanted to bend that light even more? A bigger angle? Well, that ray would have to cross the line much sooner, right? Which means a shorter focal length gives you a stronger bend. And a stronger bend, well, that means higher power.
And you know what? The math behind this is it's so simple and elegant. The power, P, is simply 1 divided by the focal length, F. That's it. They have an inverse relationship. The shorter the focal length, the bigger the power. The longer the focal length, the smaller the power. This little formula is the key to pretty much everything we're going to talk about.
Okay, but a number is no good without a unit, right? Just like we measure distance in meters or feet, well, lens power has its own special unit, and it's a word you've definitely seen before.
Yep, it's the diopter, represented by that capital D. This is the D from your glasses prescription. Now here is the absolute #1 rule you cannot forget. For our formula, P equals 1 over F. To work, the focal length F must, I repeat, must be in meters, not centimeters, not millimeters, meters. So a lens that has a focal length of exactly 1 meter has a power of 1 diopter. Simple as that.
Let's run through a quick example just to lock this in. Let's say we have a lens and its focal length is positive half a meter, so plus 0.5 meters. We grab our formula, P equals 1 over F. We pop in the value. P is 1 divided by 0.5. And what do you get? You get positive 2.0 diopters. See? It's really that straightforward. So, what about that plus sign we just saw? What does that mean? Well, this is super important. A positive power means you have what's called a converging lens. You can see it on the left. It's convex, thicker in the middle, and it bends light rays inward. This is what's used to correct farsightedness. On the other hand, a negative power means you've got a diverging lens. That's the one on the right. It's concave, thinner in the middle, and it spreads light rays out. This is for correcting nearsightedness. All right, so a single lens makes sense now. But most of the cool optical stuff we use, cameras, binoculars, telescopes, they don't use just one lens. They use a whole bunch of them, working as a team. So how does that work?
Exactly. I mean, think about it. How on earth do we figure out the total power, or what the final image will look like when light has to pass through, 2, 3, maybe even more lenses all lined up? You might think the math is going to get really complicated, but there's a very neat trick to all of this. Well, the way it works is actually pretty cool. Think of it like a relay race for light. The first lens takes the light from the original object and forms an image. Then, for the second lens, that image becomes its new object. The second lens doesn't really care about the original thing. It only sees the image that the first lens made for it. It's like each lens is handing off a modified version of the light to the next one in line.
So how do we calculate the final result of this light relay? You might think it's going to be some crazy formula, but this is where using the concept of power becomes, well, it's just brilliant.
Okay, so if you insisted on only working with focal lengths, the formula to find the total effective focal length would look something like this. 1 over F equals 1 over F1 plus 1 over F2, and so on. I mean, it works.
But look at all those fractions. It's kind of clumsy.
But wait a second. Remember our beautifully simple formula? P equals 1 over F? So what is that messy fraction formula really telling us? It's telling us that the total power of the system is just the sum of all the individual powers. You just add them up. A +2 diopter lens next to a +1 diopter lens just acts like a single +3 diopter lens. No fractions, no fuss. It's an incredibly powerful shortcut.
So why go to all this trouble of stacking lenses? Well, there are some huge advantages. For one, it lets you achieve really high magnification, because the total magnification is the product. You multiply the individual ones together. It also helps designers correct for all sorts of little imperfections, which makes the final image way sharper and clearer. And this, right here, is the fundamental idea behind how we build cameras, microscopes, and telescopes. Okay, that was a whirlwind tour, wasn't it? From a single number on a prescription all the way to the basic design of a telescope. So let's just pull it all together and create our own little optics toolkit with the absolute essentials.
Really, it all boils down to these 4 key ideas. First, the big one, lens power. P equals 1 over F, and remember, F has to be in meters. Second, our unit is the diopter, positive for converging lenses, negative for diverging ones. Third, and this is the really elegant part, the total power of lenses in contact is just a simple sum. You add them up. And finally, for magnification, you don't add, you multiply. With just these 4 rules in your toolkit, you can understand the basics of almost any optical instrument out there.
So there you have it. You've got the rules, you've got the toolkit. It isn't some kind of unobtainable magic. It's just really elegant physics. The next time you pick up a magnifying glass or look through some binoculars, you'll actually know what's happening. So I'll leave you with a question. Now that you know how it works, what could you design?